The mysterious ninth planet. Fact, fiction, or just a math trick? Part 1. The history of Planet X searches. The idea of a hidden planet lurking in the outer solar system is far from new. For centuries, astronomers have grappled with anomalies in the orbits of known celestial bodies, often proposing unseen gravitational influences as the cause. This quest began in earnest after Uranus's discovery, as its eccentric path hinted at a larger, undiscovered neighbor pulling at it from afar. This pursuit led directly to the successful prediction and observation of Neptune, a monumental triumph for celestial mechanics. Even after Neptune's discovery in 1846, slight discrepancies persisted in its orbit, fueling speculation about yet another, more distant giant. This hypothetical world was christened Planet X, representing the unknown variable in the gravitational equations. The most prominent advocate for Planet X was Percival Lowell, a wealthy American astronomer who dedicated considerable resources to its photographic search from his observatory in Flagstaff, Arizona, hoping to cement his legacy in planetary science. Lowell's meticulous but ultimately fruitless searches for Planet X continued for years, even beyond his death in 1916. His calculations, based on the perceived perturbations of Uranus and Neptune, guided the observatory's efforts. While his specific predictions for Planet X's location proved incorrect, the institutional momentum he created directly led to a significant discovery within our solar system in the subsequent decades, albeit not the planet he originally envisioned. The breakthrough came in 1930 when Clyde Tombaugh, working at the Lowell Observatory, identified a faint, moving object in his photographic plates. This discovery, initially celebrated as Planet X, was later named Pluto. For over 70 years, Pluto held its status as the ninth planet, fulfilling the long-held desire for another distant world. However, its small size and unusual orbit eventually prompted a re-evaluation of its planetary status. The scientific understanding of Pluto evolved significantly with further observations. Its diminutive mass, far less than what would be required to exert a substantial gravitational tug on Neptune, eventually cast doubt on its identity as the long-sought Planet X. The discovery of numerous other icy bodies in the Kuiper Belt, including objects comparable in size to Pluto, further complicated its classification, and ultimately led to its redesignation as a dwarf planet in 2006. This reclassification, though controversial among the public, effectively closed the chapter on Pluto as the solution to the Planet X mystery. The original orbital anomalies that prompted Lowell's search were later found to be largely statistical artifacts, or attributed to more precise measurements of Neptune's mass. However, the spirit of the Planet X hunt did not die. It simply shifted, propelled by new observational data from the farthest reaches of our solar system, sparking a renewed and more robust search. Part 2. Strange orbits at the edge of the solar system. The outer reaches of our solar system, beyond Neptune, are home to a vast population of icy bodies, collectively known as the Kuiper Belt, and the more distant scattered disk. These regions were once thought to be relatively uniform, populated by objects moving in predictable, nearly circular orbits. However, as telescopes improved and more of these distant worlds were discovered, astronomers began to notice something peculiar about their movements. A subset of these extreme trans-Neptunian objects, or ETNOs, displayed highly eccentric and elongated orbits that seemed to cluster together in an unusual way. Instead of being randomly oriented, their orbital paths, particularly their perihelia, the point in their orbit closest to the Sun, appeared to align in a similar direction. Moreover, their orbital planes were often tilted at unusual angles relative to the main plane of the solar system. exhibiting a phenomenon called high inclination. This observed clustering was not easily explained by the gravitational influence of the known planets alone. Standard gravitational models predicted a much more random distribution of these distant orbits. The statistical likelihood of such a tight alignment occurring by chance was calculated to be very low, sparking significant interest and debate within the astronomical community. It suggested that an unseen force was subtly shaping these remote trajectories. One of the most striking examples of this clustering involves objects like Sedna, a dwarf planet with an extremely elongated orbit that takes it thousands of astronomical units from the Sun. Its perihelion is too distant to be significantly affected by Neptune's gravity, making its eccentric path particularly puzzling. The collective alignment of Sedna and other similar ETNOs provided some of the earliest compelling hints of an external gravitational perturber. The argument of perihelion of these objects, a technical term describing the orientation of their orbits, was also observed to be strangely correlated. This specific alignment, coupled with the similar inclinations, pointed towards a common gravitational influence. It was as if these distant, icy worlds were being herded or shepherded by an unseen gravitational force, forcing them into these unusual configurations. These peculiar orbital alignments were not isolated to just a few objects. As more ETNOs were discovered and their orbits precisely measured, the patterns strengthened. The statistical significance of this clustering grew, making it increasingly difficult to dismiss as mere observational bias or random chance. The scientific consensus began to lean towards the need for a substantial, undiscovered mass to explain these observed orbital characteristics, breathing new life into the Planet X hypothesis. Part 3. Evidence from mathematical models. The concept of Planet 9 largely stems from sophisticated mathematical modeling and statistical analysis, rather than direct observation. Astronomers began constructing computer simulations to explore what kind of gravitational influence could account for the peculiar clustering of distant Kuiper belt objects. These models served as a powerful tool to test hypotheses and predict the properties of a potential unseen perturber. Konstantin Batygin and Mike Brown, two astronomers at Caltech, were instrumental in pioneering these models. Their work, published in 2016, presented compelling evidence for the existence of Planet 9. They demonstrated that a massive planet with specific orbital characteristics could dynamically sculpt the observed alignment of the ETNOs, effectively herding them into their unusual configurations through long-term gravitational interactions. Their simulations showed that a planet roughly 5 to 10 times the mass of Earth, orbiting the Sun at an average distance of about 400 to 800 astronomical units, could provide the necessary gravitational explanation. This hypothetical planet would have an eccentric and inclined orbit, similar to the clustered ETNOs but in an anti-aligned configuration. This anti-alignment is crucial, as it provides stability to the smaller objects through orbital resonance. The mathematical models not only explain the clustering of perihelia and orbital inclinations, but also predicted the existence of a population of high-inclination objects that orbit perpendicular to the main plane of the solar system. Such objects, some of which have indeed been discovered since the initial prediction, lend further support to the Planet 9 hypothesis as a gravitational sculptor. The strength of this evidence lies in its ability to explain multiple observed anomalies with a single, coherent hypothesis. The models provide a comprehensive framework that ties together the seemingly disparate orbital characteristics of numerous distant objects. While these are statistical correlations and predictions, the predictive power of the models is a hallmark of robust scientific theory, guiding observational searches for confirmation. Critics of the hypothesis have attempted to find alternative explanations, such as observational biases or the cumulative gravitational effects of many smaller, undiscovered objects. However, rigorous statistical analyses have largely ruled out these alternatives, suggesting that a single, massive perturber remains the most parsimonious and statistically favored explanation for the observed orbital architecture of the outer solar system. Part 4. Theories of a hidden giant planet. The leading theory posits that Planet 9 is a distant gas or ice giant, perhaps resembling a super-Earth or mini-Neptune, a class of planets common around other stars but currently missing from our own solar system. Its immense distance from the Sun, hundreds of times farther than Earth, would make it incredibly faint and challenging to detect, even with powerful modern telescopes. This explains why it has eluded direct observation for so long. One prominent idea suggests that Planet 9 formed much closer to the Sun, perhaps in the same region as Jupiter, Saturn, Uranus, and Neptune. During the chaotic early stages of the solar system, as the giant planets migrated and interacted gravitationally, this fifth giant could have been ejected from the inner solar system, flung into a highly eccentric and distant orbit, where it has resided ever since. Alternatively, Planet 9 might have formed directly in the outer solar system, beyond the known giant planets, from the sparse material available in that frigid region. This in situ formation scenario would require specific conditions and a sufficiently dense disk of material to allow a planet of its proposed size to coalesce so far from the Sun, a process that is less understood given the vast distances involved. Another intriguing possibility involves stellar capture. The Sun was born in a cluster of stars, and early in its history, it could have gravitationally captured a rogue planet from a passing star system. This captured world would then have settled into a stable, albeit distant and eccentric orbit around our Sun, becoming Planet 9. This scenario offers a way to acquire a substantial planet without requiring in situ formation or ejection from the inner solar system. The proposed mass of Planet 9, roughly 5 to 10 Earth masses, places it in an interesting category. It is more massive than Earth, but less massive than the ice giants Uranus and Neptune. This intermediate size makes it a fascinating target for study, as understanding its composition and atmospheric properties would provide valuable insights into planetary formation processes, both within our own solar system and beyond. Regardless of its exact origin, the existence of such a massive planet would significantly alter our understanding of the solar system's formation and evolution. Its presence would imply that our planetary neighborhood is more diverse and dynamic than previously imagined, with implications for the stability of other distant Kuiper Belt objects, and even the long-term history of cometary bombardment within the inner solar system. Part 5. Could it be a failed star or black hole? While the dominant hypothesis for Planet 9 points towards a substantial planet, some more exotic and less probable theories have also been proposed to explain the observed gravitational anomalies. One such idea, quickly gaining traction in fringe discussions, suggests that the unseen perturber could be a primordial black hole, a remnant from the very early universe that is not associated with the collapse of a massive star. A primordial black hole, if it exists in the outer solar system, would be microscopic in size but possess a mass equivalent to several Earths. Such an object would exert a gravitational pull consistent with the mathematical models for Planet 9. However, detecting it would be incredibly challenging, as it would not emit any light or other electromagnetic radiation, making traditional telescopic searches futile. The presence of a primordial black hole would revolutionize our understanding of black holes themselves and potentially offer insights into the early universe. Its existence would challenge current models of black hole formation, which primarily focus on stellar collapse. However, the probability of such an object being precisely located in the outer solar system and causing the specific orbital clustering remains extremely low. Another, slightly less exotic but still speculative, alternative is that Planet 9 could be a failed star, a brown dwarf. Brown dwarfs are objects more massive than gas giant planets, but not massive enough to ignite sustained nuclear fusion in their cores, making them dimmer than stars, but brighter and larger than typical planets. A very faint, cool brown dwarf could potentially exist undetected at immense distances. However, the proposed mass range for Planet 9, 5 to 10 Earth masses, is generally below the typical mass range for brown dwarfs, which usually start at around 13 times the mass of Jupiter. While theoretical boundaries can sometimes be blurry, a brown dwarf massive enough to sculpt the Kuiper Belt objects would likely be detectable by infrared telescopes, even at great distances, yet none have been clearly identified in that region. Ultimately, while these more exotic possibilities are scientifically intriguing, the planetary hypothesis remains the most parsimonious and statistically favored explanation. The known physics of planet formation and gravitational dynamics make a distant, massive planet a much more probable candidate than a primordial black hole or a brown dwarf that falls outside typical mass ranges, though scientists remain open to any direct observational evidence. Part 6. Telescope scanning the outer dark. The search for Planet 9 is an enormous undertaking, primarily relying on the largest and most sensitive telescopes on Earth and in space. Given the predicted immense distance and faintness of the hypothetical planet, detecting it requires specialized techniques and persistent, wide-field surveys that can cover vast swaths of the sky. It is a true needle-in-a-haystack search, pushing the limits of current observational technology. Ground-based observatories equipped with wide-field cameras are crucial in this hunt. Telescopes like the Subaru telescope in Hawaii, with its hypersuprime cam, are capable of surveying large areas of the sky with high sensitivity, searching for faint moving objects. These surveys involve capturing multiple images of the same region over time, and then looking for subtle shifts in the positions of celestial bodies against the background of stationary stars. Space telescopes, such as NASA's Transiting Exoplanet Survey Satellite TESS and the now-retired Wide Field Infrared Survey Explorer WISE, have also contributed to the search, albeit indirectly. While TESS primarily focuses on exoplanets, its extensive sky coverage provides data that can be analyzed for distant solar system objects. WISE, with its infrared capabilities, was particularly good at detecting cooler, fainter objects that might escape visible light surveys. The Vera C. Rubin Observatory, currently under construction in Chile, promises to be a game-changer in the search for Planet 9. Its Legacy Survey of Space and Time, LSST, will repeatedly image the entire southern sky with unprecedented depth and frequency. This vast dataset will be ideal for detecting faint, moving objects, and its advanced data processing capabilities will make identifying a distant planet much more efficient. However, even with these powerful instruments, the search is incredibly challenging. The predicted brightness of Planet 9 is at the very edge of detection for many telescopes, meaning only the largest and most sensitive can hope to glimpse it. Furthermore, the sheer volume of data generated by these surveys requires sophisticated algorithms and machine learning techniques to sift through millions of objects and identify potential candidates. The search is not just about raw power. It also involves clever observational strategies. Astronomers are focusing on regions of the sky predicted by the mathematical models, narrowing down the vast search area. The ultimate goal is to obtain multiple observations of a candidate object, confirming its motion across the sky and allowing for the precise determination of its orbit, which would be the definitive proof of its existence. Part 7. Dwarf planets and the scattered disk. The region beyond Neptune is not empty space. It is a dynamic and densely populated area containing countless icy bodies, remnants from the solar system's formation. This vast expanse includes the Kuiper Belt, a donut-shaped region extending from about 30 to 50 astronomical units from the Sun, and the even more distant scattered disk, whose objects have highly eccentric and inclined orbits. Dwarf planets like Pluto, Eris, Makemake, and Haumea reside within these outer regions. These objects are massive enough to be spherical due to their own gravity, but have not cleared their orbits of other debris, distinguishing them from major planets. Their discovery dramatically altered our understanding of the solar system's composition and the sheer number of substantial worlds beyond Neptune. The objects in the scattered disk are particularly interesting for the Planet 9 hypothesis. Their highly eccentric orbits, often taking them hundreds or even thousands of astronomical units from the Sun, make them ideal probes of the gravitational environment in the far outer solar system. It is the clustering of these distant scattered disk objects that provides the primary evidence for Planet 9's existence. These extreme trans-Neptunian objects are thought to have been scattered into their distant, eccentric orbits by gravitational interactions with the giant planets, particularly Neptune, during the early history of the solar system. However, their current orbital alignments suggest a more recent or ongoing gravitational influence, leading to the Planet 9 theory. Studying these dwarf planets and scattered disk objects provides crucial context for the Planet 9 search. Their distribution, orbital characteristics, and compositions offer clues about the formation and evolution of the outer solar system. If Planet 9 is found, it would inevitably reshape our understanding of how these smaller, icy worlds ended up in their current configurations. The discovery of more and more of these distant, icy worlds continues to refine our statistical understanding of the outer solar system. Each new object with an unusual orbit adds to the dataset, either strengthening the case for Planet 9 or potentially offering alternative explanations. This ongoing process of discovery and analysis is fundamental to solving the mystery of the solar system's outermost reaches. Part 8. Media hype versus scientific caution. The prospect of discovering a new planet in our solar system naturally generates immense public interest and media attention. Headlines often sensationalize the findings, portraying Planet 9 as an almost certain discovery, with its existence practically confirmed. This enthusiasm, while understandable, often outpaces the cautious and rigorous nature of scientific inquiry. Scientists, particularly those involved in the research, typically maintain a much more reserved stance. While the mathematical evidence for Planet 9 is compelling, it is still indirect. The gold standard in astronomy is direct observation and independent verification. Until Planet 9 is actually seen, photographed, and its orbit precisely measured, it remains a hypothesis, albeit a very strong one. The scientific process thrives on skepticism and attempts to falsify hypotheses. Researchers actively explore alternative explanations for the observed orbital anomalies, scrutinizing data for potential biases, observational limitations, or overlooked physical phenomena. This critical self-assessment is fundamental to ensuring the robustness of any scientific claim, no matter how exciting. Media reports often focus on the most dramatic aspects of a discovery, highlighting the planet-hunting narratives and the potential impact on our understanding of the cosmos. While this can inspire public engagement in science, It can also lead to misconceptions if the nuances of scientific uncertainty and ongoing debate are not adequately conveyed. The history of Planet X searches itself serves as a cautionary tale. The initial excitement surrounding Pluto's discovery as Planet X eventually gave way to its reclassification, as more accurate measurements and further discoveries refined our understanding. This demonstrates the iterative and self-correcting nature of science, where theories evolve as new evidence emerges. For astronomers, the search for Planet 9 is an exercise in meticulous observation, data analysis, and rigorous statistical testing. The scientific community patiently awaits the definitive visual confirmation that would elevate Planet 9 from a compelling hypothesis to an established fact, a process that requires significant time, resources, and often a touch of luck. Part 9, Planet 9 in Conspiracy and Pop Culture. The concept of a hidden planet at the edge of our solar system has resonated deeply within both scientific discourse and the broader public imagination, often spiraling into various conspiracy theories and finding its way into popular culture narratives. This blend of scientific speculation and cultural interpretation highlights humanity's enduring fascination with the unknown. One of the most persistent conspiracy theories related to a hidden planet is Nibiru, often linked to ancient Sumerian texts. Proponents of the Nibiru cataclysm theory claim that a massive, dark planet on a long orbit periodically passes close to Earth, causing widespread destruction. This theory predates the scientific Planet 9 hypothesis and is widely discredited by mainstream astronomy, lacking any observational or scientific basis. The scientific concept of Planet 9, despite its grounded mathematical evidence, has inevitably been absorbed into some of these existing conspiracy narratives. While distinct from the Nibiru theory, some individuals attempt to conflate the two, misinterpreting scientific papers or pronouncements as proof of an impending planetary collision, leading to undue alarm. In popular culture, the idea of a distant, undiscovered world frequently appears in science fiction. From novels and films to video games, mysterious ninth planets often serve as plot devices, home to ancient civilizations, exotic life forms, or powerful artifacts. This reflects a human desire to fill the unknown voids of space with imaginative possibilities, exploring what might lie just beyond our current reach. The evocative nature of Planet 9 itself, hinting at a hidden giant, lends itself well to storytelling. It taps into the ancient human drive to explore and understand our cosmic neighborhood, echoing the sense of wonder that accompanied the discovery of planets like Uranus and Neptune centuries ago. It represents the potential for fundamental shifts in our understanding of our own solar system. The distinction between rigorous scientific inquiry into Planet 9 and its portrayal in popular culture or appropriation by conspiracy theories is crucial. While the scientific search is driven by data and observation, public narratives often blend facts with speculation, fears, and hopes, showcasing the powerful interplay between science and society. Part 10. What finding it would mean for astronomy. The discovery of Planet 9 would represent a monumental achievement in astronomy, fundamentally reshaping our understanding of our own solar system. It would be the first major planet discovered since Neptune in 1846, marking a significant milestone in our exploration of the cosmic neighborhood and demonstrating the power of indirect gravitational evidence. Finding Planet 9 would validate the mathematical models and statistical analyses that predicted its existence, showcasing the power of computational astronomy. It would confirm that the orbital anomalies observed in the Kuiper Belt objects were indeed caused by a massive perturber, strengthening our confidence in similar methods used to infer the presence of exoplanets around distant stars. The direct observation of Planet 9 would open up an entirely new field of study. Astronomers could then begin to characterize its size, mass, composition, and atmospheric properties, providing invaluable data on planetary formation processes. It would offer a unique opportunity to study a planetary class, super-Earth or mini-Neptune, that is common in other star systems but currently unrepresented in our inner solar system. Its existence would also have profound implications for the overall architecture and evolution of the solar system. It could shed light on the dynamics of the early solar system, potentially confirming theories of planetary migration or stellar capture. Understanding its gravitational influence would allow for more accurate models of the entire Kuiper belt and the scattered disk, explaining the stability of their orbits over billions of years. The discovery would undoubtedly spur further exploration of the outer solar system. Future missions might be conceived to send probes to Planet 9, much like the New Horizons mission to Pluto, offering humanity an up-close look at this distant, enigmatic world. Such a mission would provide unprecedented insights into its formation, geology, and potential for subsurface oceans or other intriguing features. Ultimately, finding Planet 9 would expand our cosmic census, confirming that our solar system is even more diverse and complex than previously thought. It would reignite public interest in planetary science and inspire a new generation of astronomers and space explorers, proving that even in our well-studied solar system, profound discoveries still await those who dare to look beyond the known.